Okay. So is it okay? Do you see my screen? Leo? Okay. So as Leo said, if you have any questions, since you are all mute, you can write down the slide. You ask it on the chat, and I will try to answer at the end of the presentation. So today we'll talk about deep generative models, and I will start with a quote from Richard Feynman, famous physicist, who said, "What I cannot create, I cannot understand." He was a very smart guy, so he was creating math to explain the physical phenomenon that we observe in nature. And for a deeper understanding, of course, he was creating the equations by himself. And if the generative models could speak, they would say, what we understand, we can create. So before I start, I just want to do a little bit of marketing for generative models. So I start with some code, something what I found on OpenAI blog. OpenAI is a company that released GPT-3, which is a state-of-the-art in text generation, or if you want, storytelling. And they said that generative models are one of the most promising approaches toward computers that understand our world. Another quote is from Yann LeCun. It's not really on generative model, it's on GANs, Generative Adversarial Neural Networks. So Yann LeCun won Turing Award last year. Is the highest medal or the highest prize in computer science in the world. And he's a very famous researcher in deep learning. And he said about GANs that these are one of the most, or the most interesting idea in machine learning in the past 10 years. So GANs, they're not so old. They were invented in 2016 by Ian Goodfellow from University of Montreal. So the presentation today, I split it in several parts. First, I start with what are deep generative models. Then I'll talk what they are good for. I'll provide some use cases. Then I'll go towards some principles behind them. Then I'll talk on how to evaluate the quality of generated data. And I'll finish with some challenges in the field. So what are generative models? The simplest definition is a generative model simulates data generative process. But if you are an engineer or a physicist, you know that we have developed, or researchers have developed simulators based on ordinary or partial differential equations. We have graphical models. We can simulate, if you want, for example, how the light is propagating to an optical fiber, because we know physical phenomenon that, and we have the equation that can explain the world, like for reflections, refractions, and so on. Or we can build a simulator for the collision of two galaxies, for example, because we know the laws of physics, gravity, etc. But I won't talk today on these types of data generative processes, because what we have today and what it's working very good is deep learning. So we try to use statistical generative models. What is a statistical generative model? Well, it's a model where we want to learn a probability distribution P of X. For this, we need some data. So just small things to add. I will be biased. My presentation will be biased towards image generation and video, because I'm working in this field. So it will be less on other types of generation. So we need data like images. We will put in the models our prior knowledge. this won't be like physics phenomenal or our understanding of the world. It will be in the form of parametric form, the type of neural networks that we use, what loss function we use, how we optimize. So these are our priors that we'll put in the models. So if we give images to a probabilistic generative model, what we want to assign in the end, it's a probability P of X for an image to be, for example, a bedroom. And if we did our job good, then if we can sample from P of X, and we can generate new data. New data meaning data that our model didn't see during the training procedure. So what are deep generative models? Well, we know that deep neural networks, they are very good in extracting patterns from the data, but we don't want just to extract patterns. We want to use those patterns to learn the underlying probability distribution of the data and use it to generate new data. And for this, we use deep neural networks, as I said. And the idea is we want to convert the generation problem into a prediction one. And for this, we want to use deep neural networks. So in machine learning, there are two paradigms. One is the so-called discriminative machine learning, and the other is called generative machine learning. And they are connected to each other. So all this hype, let's say, with deep learning started around 2011, 2012, because of the success of discriminative models. So as you can see here, I gave a few examples. Discriminative models, what do? They are good, for example, for classifying images. Does this image contain a cat or a dog or a bicycle, etc. Or they're good to detect objects in images, or we can do semantic or instant segmentation, as in the last image here. But all of these types of learning are in the supervised setting. What does it mean, supervised setting? We need the training set of images where we have the true label. We train a deep neural network to learn a mapping from images to labels. And then we use this neural network with other data set or other images that it didn't see during training, and we hope that it will produce the correct label, the predicted label this time. So this is supervised learning and discriminative. So that is what we want. The goal is to learn a conditional distribution. For example, giving this image here, which is a bedroom, for example, what is the probability of the label to be the bedroom? And what we want, in fact, is it's enough to find a decision boundary between the images or the features. In the generative setup, we have to learn a more difficult problem, because what we need, we don't have the images X. What we need to learn, it's a joint probability distribution of labels and data. So the two are related, as I said before, through what is called Bayes' rule. So the term in the left, probability of Y equal a bedroom given this image, this is the discriminative part. The denominator P of Y given a bedroom, comma X given this image, this is the joint probability distribution. And this is the generative part. So if we learn this harder object, the joint, then we can do also discriminative. So if we learn a generative model, we can also do discrimination. And we divide by the marginal probability P of X given the image. So in the generative model, there are several, I try to classify them, let's say. So we have likelihood-based frameworks. where there are different methods. I only say 3 of them, some of the most popular today. They are the autoregressive models, variational autoencoders, flow models. Then there are 2 non-likelihood-based frameworks. One is generative adversarial neural network, and the other it's a new method based on score function, and they estimate the gradients of the data distribution. The most popular methods, according to Max Welling. Max Welling is co-author or co-inventor of variational autoencoders. So today the most popular are GANs, generative adversarial neural networks. Then there are VAEs and flows. Today I will talk about GANs and VAEs. And what I just want you to keep in mind is that there are people trying to make to join different types of methods, like making a unified framework for VAEs and flows, or unified framework for VAEs and GANs. So it's a blurry, it's not, this classification doesn't have to be exact. Okay, so what they are good for, at least to understand the reason. So if I was in a class, or if we were in the same room, I would ask you if you think these images are real or fake, or tell me which one is real and which one is fake. But since we are online and you're all mute, I cannot answer. I cannot ask this question. So I will directly tell you that these are all fake or synthetic images. These faces do not exist in the real world. So that means that they are good to generate images. They're also good to generate sound. And I will put you some generated audio now. In a second. For me, this one, it sounds very realistic. I couldn't say that it's generated. And yeah, it sounds like Chopin for me, but not really. Also generated. So I will make the presentation available online, and you have all the sources here, or the articles, or where I found this information. And if it's from a course from a university, I might type the course name. They're also good in generating text. And this is some text generated by GPT-3 from OpenAI. Again, I couldn't say it's a generated text. In a shocking finding, scientists discovered a herd of unicorns living in a remote, previously unexplored valley in the Andes Mountains. Even more surprising to the researchers was the fact that the unicorns spoke perfect English. So yeah, it captures even the grammar of the language. I would say it's very, very realistic. What can we do with them? Well, there are a lot of applications. I'll just give you some, and I hope to get you interested in this and try to investigate or apply if you need at your work. So in the left upper corner, we can draw a sketch of a face, and we can generate like a cartoon. Then we can take faces, we can learn a mapping from real faces to cartoon faces. We can cartoonify the faces. Then we can apply different styles of painters to some photos. So we can take photos with our camera and apply Monet style, and it will transfer the style of Monet. We can transform zebras to horses and horses to zebras with some other architecture. Or we can transform a photo taken in summer in a photos taken in winter or day, transform it in night. and many, many other types of image manipulations. It is very, very interesting. Other use case we can use to debias data sets. For example, we know that in a majority of data sets with faces, they are white adult males and less other ages or other races. So we can find the biases in the data sets, or we can use it to generate undersampled images to generate more. Or we can use to augment data set. And another use case, for example, we can use it to do what is called anomaly detection, because with generative networks, we can do density estimation. What does it mean, density estimation? Since we learned the underlying probability distribution, we can also say this has a low or a high probability to happen. As a use case, I gave something that I was interested some time ago, how to detect people that fall. And we don't have enough data with falling people, but we have a lot of data with people doing daily activities like walking, sitting, drinking, eating inside the home. So in order to preserve privacy, it was used for this problem thermal camera, so we cannot see the faces and cannot identify the people. And the researchers, they had some falls and a lot of daily activities. So they did density estimation and they used this to detect anomalies. And one type of anomaly is someone falling in his living room, for example. Now I will go to some principles behind the generative models, and I will use variational autoencoders and generative adversarial neural networks. GANs. Before of that, I want to explain what is a latent variable, because we will cross this notion in a few slides. And I found this very interesting, very nice explanation in a course on deep learning from MIT. And they explain this with the myth of the cave. So this is a story from Plato's Republic, from Plato, where we have some prisoners. They are caught inside the cave. So they are behind the wall. They are maybe with chains. They cannot move. They can only see some shadows on the wall, as you can see in this picture. And the shadows, they are not real objects. We know that the real objects are the persons on the other side of the wall, walking with those sticks with the animal. But the light produces these shadows. So for the prisoners, the real objects are the shadows, but they are just an effect on some real latent variables now, which are the true objects, but we don't have access to the true objects. I hope it is clear. So we have real object producing an effect, only that we can see is the effect. And we try, by observing the effect, to imagine how the real object looks like. And we use this in generative models. And we can also classify like the models being latent variable models. And from this point of view, GANs and VAs are in the same type of generative models. So I'll start with autoencoders, the simplest generative models that are very simple that we can build. And how do we train? What is an autoencoder? We use two neural networks and a data set that we want to reproduce, okay? The simplest data set in machine learning to start with is MNIST, which is handwritten digits. We have 60,000 small images, 28 by 28 pixels with handwritten digits. So we feed this data to an encoder, which is a neural network, a deep neural network. But what it does, it compresses the data tries to find these latent variables, and we put them in a vector Z, all of these latent variables. And then we use another neural network, which is called a decoder, which upsamples the latent space Z, and it tries to reconstruct the original image. So it's like a bottleneck. We try to capture the essence, the most important things under the latent variables which produce all the handwritten digits. And how we do? We just compare pixels and we compute the distance between input pixels and output pixels. And we want them to be the same. So we minimize this loss function. And this has a minimum when the pictures are the same. In reality, the output is not exactly the same as the input. We call it X hat. It's an estimate of the input. The output might be blurry because the output also depends on this Z, the dimension of the Z vector. And we can see here that we can even compress to a 2-dimension Z. So with only 2 numbers, we can capture all of the handwritten digits, but they will not be so neat, so clear at the output. A better way it is to have a vector Z of latent variables with, for example, 5 dimensions. It's closer to the ground truth, as you can see from the 2 images. Okay, so this is autoencoders, but with autoencoders we can learn the data set that is fully deterministic, because in this Z, the Z is fixed. Once learned, the weights of the 2 neural networks, the encoder and decoders, are fixed. So we cannot generate new data that it hasn't seen during the training set. So for this, we add the twist. Sorry. We add the probabilistic twist. So Z, we express it with 2 vectors. One is vectors of mu, standard deviation of a Gaussian distribution, mean, sorry, of a distribution, and variance of a distribution. So now it becomes probabilistic. So we can sample new images that we can reconstruct new images sampling on Z. So the loss function now, it has reconstruction loss and a regularization term. And I will say what do they mean. So the reconstruction loss is exactly like autoencoders, like before. We just compare input and output at the pixel level. And the regularization term is to prevent overfitting. And this is expressed with Kullback-Leibler divergence between some prior distribution that we consider, so we put our knowledge, and the distribution that we are trying to model. And why do we do this? Because, as I said, we want to avoid overfit. So we don't want the model, the neural network, to just memorize the data. And what happens when it tries to memorize the data? Well, we see in the Z space or in the feature space that we tend to cluster, to find clusters. So they're not filling all, let's say, all the space around the center of this hyperspace. So then we say, no, you should try to go in all the direction, not to memorize the data. And for this, we use a multivariate Gaussian distribution. And then I have to explain you what, in fact, is this Kullback-Leibler divergence. Okay. So as I said, we have a prior, which is the Gaussian, multivariate Gaussian, and we are forcing our distribution, the Laurent distribution, to minimize the divergence between the Z and the prior. And KL divergence, what it does, in fact, it's a measure of how two probability distributions are different or not. So I'll give you two examples. We have two Gaussians. One is centered in 0 and it has variance of 1, and the other is centered in 1 and it has variance of 1. Okay, so we want to see how different they are. The Kullback-Leibler divergence, it's a number, it's not a distance, it's a positive or 0 number. And we have another example where we have two Gaussians. One is centered in 0 and the other in 1, like in the previous case, just that the variance is 100 for the two. And we are thinking, if we just consider the parameters mu and sigma for the two Gaussians, then they should be the same. But our intuition tells us that the ones with variance 100, the difference in the two should be smaller, as we can see visually in these two plots. So then the Kullback-Leibler, the KL divergence, is computed as it is here represented in the formula. It's an integral of q of x logarithm qx divided by p of x dx. So what does it mean? It means that we compare for each point on the x-axis the two distributions, and what we want is to have a small difference between the two different small average distance across all the points on the x-axis. And if we compute like this the KL divergence, we find out that the KL for the first case is 0.5 and for the second case is 0.005. So the two distributions are more close related when the variance is 100 than when the variance is just 1, as we were expecting. So this is just to explain the KL divergence used from the prior here at the regularization term between the prior, the Gaussian multivariate, and the distribution learned in the Z. Okay, but there is a problem with this Z, with this probabilistic twist. Well, we cannot train an end-to-end model with this because we have to do backpropagation. That means we have to compare the output with what we were expecting and backpropagate gradients. But it's not possible to do it through Z because of these two random parameters, mu and sigma. So there is a trick to solve this problem. Instead of Z computed like this, we consider a fixed Z with a fixed mu vector and a fixed sigma vector. And we add a parameter epsilon, which is drawn from a probability distribution, to this sigma. But I think more easy is to understand with this, picture. So blue squares are the deterministic node and yellow or red circles are the stochastic nodes. In the original form, we cannot backpropagate. We stop at Z because we have to store for backpropagation. But if you draw a random sample, we cannot store for the backprop. But in the second, in the reparameterized form, we took outside this backprop chain, we took outside epsilon. So then we can backprop because everything is it's fixed Z, and so mu's and sigmas are fixed. Okay, So I come back to this Z. How does it look like, and how can we evaluate, for example, this Z? We can perform some analysis on this Z by keeping all the parameters fixed, or all the numbers inside except of one, and we vary one parameters, and we see what is the effect on the output image. So doing that, we can find very interesting things. For example, we can have one latent variable responsible for head pose. So just modifying Z, increasing or decreasing, in the end, the image will rotate the head. The same can be with the skin color, or if we use the MNIST handwritten digits, we go over similar, let's say, looking digits. Okay, so this is with variational autoencoders. Now, a few words on generative adversarial neural networks, which is a likelihood-free type of learning. And this is the coolest idea in the past 10 years in machine learning. I'll say a few words on how they work. I just want to add something before I dive into explanation, that this meetup will be just on introduction part, but next month or the next months we'll have other meetups where I will dive deeper in variational autoencoders and GANs. So I'll take them again and explain more in detail and with some code or some demo to see. So I just want you to have an overview image of variational autoencoders and GANs. So GANs, how do they work? Well, in GANs, we have two computing neural networks. One is called generator, and the other is called discriminator. So they fight one against each other. The generator takes random noise, as you can see here at number 2, and it tries to transform random noise into realistic looking images. The discriminator has access to real images, like number 1, and generated images. And he has to decide, it's a binary classification problem. Is it real or is it generated? Then we have a classification error and an iteration, we iterate. So this is the training process of GANs. How do we do that? Just stay a little bit here. No, I'll stay here. So at the beginning, the generator will generate very bad, let's say, images, and it could not fool the discriminator. But then we train, we back propagate, we change the weights, the parameters of the model to become better. And it will start to learn the probability distribution behind the real data. And the discriminator, in the end, it will be very hard to decide. So this is called the training process. And what do? We train separately generator and discriminator. And the generator generates a batch of images. Then we have some predictions, like any neural networks. We compare with the true responsive. We compute a loss. We modify the parameters of the generator. Then we do the same with the discriminator. And the generator with time will become better and better. And the discriminator will have difficulties to say if it was a real, it is a real or fake or synthetic image. And the question is, okay, how long do we do this? How long do we train? Well, the answer is given by the game from the game theory. I forgot the name. Okay, Nash equilibrium is the name. They reach a Nash equilibrium. What does this mean? When they have two competing networks or players in a game, there is a point when one player cannot gain anything if it changes. Each player has a strategy, okay? And there is an equilibrium where no player can improve its reward by modifying its strategy. So that means that the generator cannot improve the quality of the images, and the discriminator cannot guess better. For discriminator, it will be random guess. So then we can stop training. And but this is not so easy, let's say, because at least at the original GAN paper and original GAN architectures, there were some other problems during training. They were very hard to train because we had, we could have different reasons. One is oscillating loss function. And maybe some of you who train neural networks already have seen this. Another problem is mode collapse. What does it mean, mode collapse? Well, it will just produce some of the classes, not all of the classes. As you can see here, many ones, not so many 5 or 3 or vanishing gradient. This is a well-known problem in deep learning. Another problem, failure to converge. So it was a great idea at the beginning, but in practice, it was very hard to make them train. But the research community pushed a lot of effort, and many of these problems now are overcome with some solutions, but I won't get into details now. Okay, so now that I explain a little bit on variational autoencoders and generative adversarial neural networks, GANs, I want to address this question: how can we evaluate this? So there are several, let's say, metrics to evaluate these models, the generative models, depending on what we are searching for. For example, we can talk about the quality of the latent vector, latent representation Z, or we can talk about the quality of images, how realistic do they look like, or the quality of text or the quality of image. So now I will talk about the quality of images. And for this, at the beginning, the research community used human annotators. So they were putting data set of mixed generated and real and synthetic images, and people, they had to vote. They were looking, do you think it's real? Do you think it's fake? But researchers found out that there were some problems with this method because people, they are subjective, because their prediction have high variance. They can differ a lot among people. So that means it's hard to compare different models. You cannot compare, this is better than this. How can we say if there is no agreement among people? It might be time consuming and expensive to put people to look at tens of thousands of images. Then there is this problem with overfitting. Generative models can overfit and underfit in the same time. What does this mean? Overfit is memorizing some images, seeing during training. And this is very hard for a person to realize, because if I look at 1,000 images, how can I know that that particular cat appeared 30 times and this is also in the training set? It's very hard to know. And underfitting, it means that it doesn't generalize to new data. And this is very hard for humans to realize. One way to do it was to compare generated images, synthetic images, with some sort of distance and see which is the most similar image in the training set with that generated. So the most similar or with a small distance really generated from the training set. And then you show this to human annotator, and he will look at, he will say, do you think they are the same or not? But again, this might be subjective. So we have to find some ways to automatically detect which are, how good a model is performing. And the first, one of the first, it's not the first way to do it is what is called the Inception Score. How does it work? Well, Inception comes from the neural network called Inception V3, which was very good in classifying objects. For example, in ImageNet, which is a data set with more than 1 million images and 1,000 classes, it was very good to classify among the 1,000 classes. And we take a pre-trained network, we eliminate, we don't eliminate, and we use it to classify the objects generated by our model. So we have this assumption that this is a good classifier, okay? And what we want for our model are, in fact, two things. First thing is to be very confident about the class for generated, for example, images. So if the model, the generative model, generates images with dogs, we want this model pre-trained to be very confident to output high probability values for cat or for each class. But this is not enough, because maybe the model just learned to reproduce dogs and it doesn't know to reproduce bicycles or other class that we trained on. So we also want to have a variety, to be variate the output of the generator, to have a balance between all the classes. So these two criteria, we can combine them in one. So the first criteria, at least what I found in Stanford, they call it sharpness. They want sharpness to be high, because high sharpness will yield to high probability scores. And they want diversity to be high. And we mix them together. And again, since we have two probability distributions, one is marginal over all classes, and one is the conditional probability of label y given the image. What we mix them together, and what we want, in fact, is a high KL divergence between the label distribution and the marginal distribution, because that means we have high confidence for the class and almost uniform or more uniform for the labels. And for this, we use KL divergence, and we have what we define as Inception Score. Well, Inception Score, the higher the better it is, and depends on the training procedure, depends on the training data set. There are some problems with it. So some researchers discovered that because of initialization of neural networks, which implies a randomness, Inception Score might be different for the same architectures, because between TensorFlow, PyTorch, and Keras, there might be different weight initialization. So this is a problem. Then if we use a pre-trained Inception V3, but not an ImageNet on another data set, we might find different values for Inception Score. So that means it's hard to compare generative models. It fails to capture mode collapse. So when the image is producing same class of generative or more one class than the others inside the class. And overfitting might cause a good Inception Score. But by tradition, it's still used today, Inception Score, in research papers. A better way to assess the quality of generated images is using Frehet inception distance, or FID. And how does it work? Well, the authors consider that the coding units, I mean the activations of V3, follow a multidimensional Gaussian. And what they do, in fact, they use the pre-trained model, and they pass images through this. They just do the forward pass until a certain layer. And they use this activation from real and generated images. And then they compare the means and the covariances for the outputs. And what means this, that if you have realistic generated images, then the means and the covariance should be close to each other. So lower the FID, the better. And here I added some NumPy code. I gave the source here, how to compute this FID. And you see it's not a big thing to do. Unfortunately, there are also some problems with this method, but it is better than the Inception Score because it apparently captures better the perception of human annotators. But depends again on the ImageNet training, and it changes with the training data set. Another method is called KID, kernel inception distance, where we also have some assumption that we have two distributions. One is the real and one is the synthetic, P and Q. And if the model produces realistic looking images, then a mix, if you take separately the expected or the mean of the of real images, the expected value and the expected of synthetic, if we take a mixture of, or if we mix synthetic and real, the difference should be very, very small. But this is not really used today because it's computationally expensive to do this. So for the moment, the Inception Score and FID it's used. But recently, very recently, a research group from Stanford tried to come with what they called golden standard for evaluating generative models, and they use human annotators, but with some method imported from psychophysics, I forgot the name, from some other field of study. So what do they do? I'll just explain how do they do. They say that there is a threshold of perceivability or of perception to human annotators. So they show images with real or fake images with a certain time. They flash images. And if the human annotator is good in distinguishing real and fake, then they decrease the time until it starts to fail. And then they increase the time, they let more. And this gets the best, let's say, from the human annotators. And they say that this is the best method to evaluate, but still it uses human annotators. So there is a research paper also from Stanford where they try to approach the same results with HYPE. So this method is called HYPE, human eye perceptual evaluation. So there is another method which uses a sort of Frehet inception distance feed, but across several layers of the neural network, and in order to approach the golden standard. So these are some methods used for images to evaluate the generative models. Okay, now before the end, I will talk a little bit on the challenges in generative models. Maybe they are not all, it's what I think now are challenges. So I'll talk about two approaches, let's say, to generative data. One approach is we have, us as human beings, a lot of knowledge of our world. We know, we have a domain expertise, we know the laws of physics, so we can put all of this knowledge into models. And then this is called the inductive bias. We add data and we try to do predictions. But this is one way to do the generative models, let's say. Another way to do it, we have a lot of data and we let, let's say, deep neural networks or the model discover all of these laws in the data. And here we don't need so many domain knowledge, but we need a lot of data. So these are two different approaches. But we as humans, we don't need tons of data to, we have a representation of the world inside, we know the physics laws, and we don't need 1,000 or thousands of images with one type of animal. It can be the first time that you can see it. For example, maybe for you, for some of you, this is first time that you can see a water bear. So I don't have to show you thousands of images with this to recognize it in different postures or different images. So if I give you 3 other test examples, you can recognize the same animal, the water bear, in the first and in the third image. Even if the color is a little bit different, even if the angle is different, or the lighting conditions, or if we have shadows, all sorts of variations. So we are very, very good to capture these underlying patterns with few data. So that would be a challenge, how to do the same in generative models. Maybe how to go more to an inductive bias and to introduce the laws of physics, laws of biology, psychology, sociology. And one big advocate for causality is Judea Pearl, who said that machines, in order to become intelligent as people, like people, they have to understand causality, not only correlations in data, but also causality. And I like very much this quote from him. This ingredient, causality, should allow computer system to choreograph a parsimonious and modular representation of their environment, interrogate that representation, distort it through acts of imagination, and finally answer what if kind of question. So if I show you this picture with the water bear for the first time with an act of imagination, you can imagine it walking on the moon or on a Mars planet, even if you were never there. You can imagine it jumping, screaming, talking, and whatever, without actually seeing it, never seeing it. And this, for the moment, we are not there. And another challenge, for example, is the course of dimensionality. Because when we model some phenomena with deep generative models or generative neural networks, sometimes we have the data that we want to understand and to model is very, very high dimension. And this is hard computationally it might be very, very expensive or intractable to model. And then there is also this what's called corner cases or boundaries. Maybe we don't need to model all the data that we have in the training set in order to capture these patterns. Okay, so these are probably they're not all the challenges, but this is what I thought about and what I found. And that's the presentation. Thank you for listening. And if you have any questions, I will answer, and I will ask Leo to unmute you, or you.
Okay, thank you, Robert. I think it was a great presentation. You walk us through a lot of things. You showed us the creative genius of the researchers. They are trying to evaluate deep learning models with another deep learning models. So yeah, if there are any questions from the audience. If not, maybe somebody will ask a question. You mentioned something about unification. So
yes.
That probably will not be the same case as we have in physics.
Well, we already talked about reparameterization trick in deep learning, a term that I learned it in physics. So maybe we will have to unify all the forces, I don't know, in a single all-explaining model.
Yeah, let's hope they will do a better job. What can I say? Let's not wait 30, 40 years to do this.
This definitely no. It's a very good time for deep learning research. Unfortunately, I'm not in research, but yeah.
Okay, so I don't know, should we wait a few more minutes, or how do you think?
I think you should unmute everyone, and if someone has a question, just...
Yeah, or a free conversation, we can have a
yeah,
free conversation.
And I wanted to ask something before I forget. If there are people willing to study generative models, deep generative models, to be part of a small group but active, to go deeper into details, he or she can contact me, and we are open to, let's say we are a small group and we are open to new members. We do everything online and on a weekly basis. Doesn't have to work with generative models, but we're looking for passionate people. So yeah, feel free to write me on Meetup or whatever.
Okay, so I will give everyone the permission to unmute themselves, and feel free to jump in and discuss things, ask Robert anything that you want. We will have this recording on our Meetup channel. We will post everything, so if anybody would like to revisit what Robert has discussed, maybe for future reference for the next meetups, because he told us that we will have more meetups on this subject. Yeah, you can revisit the material and study on your own maybe a bit this concept, because it's definitely not something that's easy. So I think Wolfgang mentioned something in the chat. I know enough French to understand what he said.
I don't see on the chat.
Oh, I think he wrote to me. Okay, so I think Wolfgang mentioned that he's interested in our group, and he gave me his email. So I will pass you his email. Okay, thank you, Wolfgang. Yeah, Roberto, you can unmute yourself, I think.
Robert, please.
Yes.
So the use of the Frehet distance is mainly to optimize the network.
No, it's a way to evaluate
Evaluation of the quality.
Yes, because you have articles. They all look very realistic to me. At least the last flavors of GANs, but how can you say this is better than this? Who's the best? If they train on different data sets, so it's a way to qualitatively evaluate models.
Mm-hmm.
And it's not perfect. At least people from Hype with the gold standard with human annotators, they show that it doesn't correlate perfectly with the human perception from their point of view. But this is the thing. You want to find the automatic method to distinguish who's the best in the field, let's say.
Last question.
Yeah.
Can you explain in concept, not in math, some meaning information of the latent volume in the network?
Yes. So the idea for this latent space is to have a compact representation. It's a sort of, it's a compression of information, because we don't need and we don't want to memorize all the data. What we want is to memorize the generative factors of the data, and we can compress, and you could see with MNIST, even for two nodes, two neurons, let's say, or two numbers in the Z, you can reconstruct the data, not perfectly, but maybe for some applications you don't need lossless, let's say, compression. Maybe lossy, it's fine too. And if you want to model the world, of course, you need good latent representations.
So the volume of the latent space is like a pipe with a small section. Usually is very long because each layer is a fissure. It's a macro fissure, no? It's a dimension.
Yeah, you can see it in a hyperdimension if you want.
Mm. So try to describe me the volume, the slice, the single layer, or a single line of a single element propagation.
Yeah. I cannot describe you.
No, I know
they're just numbers.
I know it's a difficult question.
Yeah. But what you want, in fact, is to capture disentanglement. I mean, one value from this feature space to correspond to one factor of variation in the reconstructed image.
Yeah, this is why I'm asking.
Yeah, if you change one value discretely, if you change, you should see what we consider it's a high-level concept. Let's say a person turning the head or changing the skin color or doing something, but only one thing. But this is okay. Maybe it's more to talk on it. There are many articles on disentanglement, but I'll surely talk when I'll present variational autoencoders. I'll say more on disentanglement.
Okay. Thank you very much.
With pleasure.
also, Robert, is there, I mean, you mentioned stochastic nodes.
Yes.
Do we know for sure that those are stochastic nodes, or it may be something that involves chaotic processes?
No, they are stochastic because we randomly sample from a distribution that we choose.
Oh. Okay. Okay, so I guess if there's no other questions, I think we can close the meetup and close the recording. And yeah, for those who completed that survey, they will get another post-event survey, and after the completion of the latest one, you will get through the email a list. I mean, not a list, but a code, a promotional code with 50% off the first month of Coursera. So yeah, well, Robert, thank you, and we're looking forward to the next meetups.
Yeah, next month, probably on more deep in variational autoencoders or GANs, one of the two. And we'll take them, let's say, one by one from the classification slide, let's say, and dive deeper.
Okay, so I think people that are new to this meetup, if you join our group, then you will see the event. We will post it in time, so you will see that we'll have the next meetup. So yeah. Okay, thank you, Robert. Thank you all, and see you.
Thank you. Bye-bye.
Thank you.
Thank you.
Thank you.
Thank you. Bye.
Bye.
Thank you. Bye.